Professor Davis here as we move into Chapter 3. Well, remember in Chapter 2 we talked about how to describe data with charts and graphs. In Chapter 3 we want to see how we can describe data numerically. So Section 3.1 is on measures of center, one of the ways we can describe data numerically. So let me make a couple comments here before we get going. This is the portion of the course that deals with numerical descriptive statistics as opposed to graphical descriptive statistics, which is what we talked about in Chapter 2. Now the calculations we're going to be doing, remember we talked in the first chapter about the difference between statistics and parameters. In this chapter, our focus is on sample statistics. In other words, taking data from a simple random sample and computing their statistics. So we won't do much hand calculations. We'll let technology do that, and we'll focus on interpreting the solutions here. So the idea of measures of center, they tell us what a typical data item looks like in a simple random sample of data. So let's go ahead and write this down. A measure of center is a value at the center or middle of a data set. So we have 4 measures of center we want to cover. Let's go ahead and get started on them. The first measure is probably the best known of all statistical measures, something you've all computed before, the mean. And before we go any further on its computation and formula and so forth, let's talk about the notation that we'll use and we'll see throughout the rest of the course. First, if we see this Greek letter sigma here, that denotes the sum of. So that means add up all the things that we're discussing at that moment. Usually it's the sum of a simple random sample where we add up all the values. X is a variable used to represent the typical data item in a set. So when we write sigma x, that simply means add up all the sample data. N represents the sample size. And we talked about that in the previous chapter in the context of the sum of the frequencies. But now, if we simply have a sample of data, the number of data values we have makes up the sample size. And also, if we see a capital N, all right, that represents the population size. So I'll distinguish between the two in just a minute here. So let me talk about the formulas for the mean, and there's really 2 of them in this case, and we can talk about 2 of them here. First, we can say for a sample of little n data items, the sample mean is given by, well, here it is. And for this part, we say x bar. That's our notation for the sample mean. And what is it? Sigma x over n. So that means to take the sum of the data values and to divide that by the sample size, the number of data values that we have. Now, so that is a sample statistic. It happens to have a corresponding parameter. And let's talk about that for a minute. We can say for a population of capital N data items, the population mean, and notice the notation there, we use the lowercase Greek letter mu, and it's what? Mu is the sum of x times the population size. So it's the sum of the data values divided by the population size. So notice here, the formula is the same. It's simply the notation that's different. And the other important thing to remember is that in real-life situations, we often do not know the parameter of the population mean. We don't know mu, that parameter. And we're going to estimate that later on. We're going to talk about techniques where we can estimate the population mean given a simple random sample. So let's try an example where we compute the sample mean and do an interpretation here. So how about this? The following radiation levels, measured in watts per kilogram, of a sample of 11 popular cell phones is shown. There it is. All right, so we have a couple of things we want to do here. First, determine the mean of the data. And second, if the FCC, the Federal Communications Commission, has a standard that the phone must emit less than 1.6 watts per kilogram, are cell phones generally safe? All right, so think of what we want to do. First, we want to find the mean of the sample, so we're going to add up all those radiation levels and divide by the sample size, and we know the sample size is 11. So let's go ahead and get going on that. So we add the values and divide by the sample size. And notice here the sum of the data is 10.32 watts per kilogram, and the sample size is 11, so we get 0.938, and I'll talk about that number in just a minute. All right, and again, you don't have to worry about how we get this computation. We'll have StatCrunch doing this for us. All right, so let's interpret the answer here. So the mean radiation emission is 0.938 watts per kilogram. And remember what the second question was. If the cell phones must emit less than 1.6 watts per kilogram, are cell phones generally safe? Well, notice here, this number that we have, the mean, is below 1 watt per kilogram. So we can say that since the mean of the radiation emission is less than the FCC standard, 1.6 watts per kilogram, it seems that cell phones are generally safe. We can say that by taking a look at that simple random sample. So I wanted to talk for a moment just about the rounding rules for our different measures of center. So let's go ahead and write these down. Unless otherwise indicated, we want to round these measures of center, the mean, the median, and the mid-range, to one more decimal place than the given data. For example, for the mode, leave the values as they are without any rounding, and we'll talk about those measures of center in just a minute. For example, if the data is given as whole numbers, we want to round to one decimal place. All right, whole numbers have no decimals after them, so we round to one decimal place. If the data is given accurate to 2 decimal places, we round the mean to 3 decimal places. And that's just what we saw in that example just a moment ago. And we only round the final answer. One mistake we can make is to round during intermediate steps. That causes what's called a truncation error and can really take a correct answer and make it incorrect because you chop off the data. And that's one advantage of using technology to get the mean, is that we don't have to worry about those intermediate steps. So let me talk about some of the properties of the mean before we move on. First, the mean can be computed with interval or ratio level data. Remember, we had those 4 levels of data measurement we talked about in Chapter 1. They were nominal level, ordinal level, interval level, and ratio level. All right, so to compute the mean, we need those 2 highest measures of center, of data measurement. All right. A set of data can have only one mean. All right, so you can't have a set of given data items and have 2 or 3 different answers. So the mean for a given simple random sample is unique. Every level appropriate set of data has a mean. So in other words, if we're given any interval or ratio level data, we can always compute the mean for it and always get an answer. That's not true with all the measures of center that we'll see in a minute here. A data item that's much different than the other is called an outlier. And we talked about that before, and we identified them using dot plots, I think one of the ways was. Since the value of the mean can be affected by outliers, we say that it is not a resistant measure of center. It can be thrown off by these outliers. Now, one way we can get around that is to trim the mean to minimize the effect of outliers. So we'll compute a trimmed mean here later on. So the mean is not resistant to outliers because it can be thrown off by one data item that's much different than the others. One way to get around that is our second measure of center, the median. So the median of a set of data is the middle value once the original values have been arranged in order of magnitude. In other words, decreasing or increasing. The notation for the median is, we can use the capital letter M for median, MED, you'll see that on your calculator, and the traditional version is what we saw here, X tilde, all right? So X with a little squiggly line, so we use X bar, X with a line over it for the sample mean, X tilde with a squiggly line over it for the median. So determine the median by hand. we first have to sort the data from least to greatest. So let me talk about a couple of rules on determining the mean, and StatCrunch knows all these rules, and so does your calculator, by the way. First, we want to sort the sample data in order, and then, if the number of data values is odd, the median is the number located in the exact middle of the list. For example, we call that the n+1 over 2th value. So for example, if we have a sample size of 7, for example, so n is 7, we add 7 plus 1 and get 8. 8 divided by 2 would be 4. So the fourth data item in a sample size of 7 would be the median value. But what if it's odd? I guess that's the natural question. If the number of data values is even, the median is found by computing the mean of the two middle values. And again, once we put them in order. So if the data values, the sample size is odd, it's pretty easy to compute the median. If the number of data values is even, the sample size is even, we take the mean of the two middle items after they've been ranked from least to greatest. So let's just run through an illustration of this again. Here's the same data we were looking at before, the radiation levels of 11 popular cell phones, and let's find the median in this case. So the first thing we have to do, sort the data from least to greatest. All right, so I went ahead and did that. So the first data item is 0.38, then the next one is 0.50, and so on. And remember, the sample size was 11. All right, that's an odd number. So since the sample size is 11, the median is going to be what? The 11 plus 1, that's 12. Take 12 divided by 2. You're going to get the sixth value on the sorted list. So let's just count it up here. 1, 2, 3, 4, 5, 6. So it looks like 0.92 is going to be the median. All right. So that look good. So that's kind of a way to get rid of to address the notion of outliers, because we're throwing all the data values out, so to speak, and the only one that's left is the middle one. So let me talk about the properties of the median now. First, since we exclude all of the values except the middle ones, the median is not affected by outliers. Consequently, we call the median a resistant measure of center. It's not going to be thrown off if you have an outlier in your sample of data. Also, the median can be computed not only for interval or ratio level data, but for ordinal data as well. So it's possible for the median to be a word, so to speak. You know, like when we rank things like fair, good, excellent. You know, one of those could be the median if we sort all the data from least to greatest. So the median can be computed for the top 3 levels of data measurement. And the median can be determined for only discrete sets of data. And typically we want it to be a fairly finitely small number too. That's when the median works the best. So we've talked about the mean, we've talked about the median. Now let's move to the mode. The mode's kind of an interesting measure of center. It has some unique properties to it. So let's go ahead and define it here. The mode, and notice how we have it denoted, m with the subscript of 0, sometimes read m naught, is the data value that occurs with greatest frequency. So the mode is a data value. So to identify the mode, a couple of rules. First, if more than one data value has the highest frequency, then each of those is the mode. So if 2 data values have the highest frequency, both of those are the mode, and we call that data bimodal. And we can have multimodal data as well. If no values repeat in a data set, in other words, if the frequency of every data item is just 1, then we say the data has no mode. So to find the mode, I usually sort the data and then search for the repeated data values. Now what's nice is the updated version of StatCrunch that you're using also computes the mode. That wasn't true just a few months ago, so you can take advantage of that. So here's an example, same data set we were talking about. The following are radiation levels of 11 popular cell phones. Find the mode of the data. Well, notice here, let's just take a look. Now this, if you take a look here, none of the data items repeat. These two data items are very close together, 1.54 and 1.55, but they're not the same. So if you examine them for a minute, none of them repeat. Consequently, since none of the data items repeat, then there is no mode for this data. Alright, so let me talk about some of the properties of the mode, because I said some of its properties are really pretty unique. First, the mode is the only measure of center whose existence is not guaranteed for a set of data. So in other words, we just saw an example where the mode didn't exist. That's not the case with the other measures of center we had. If we had level appropriate data, we could always find a mean or a median. That's not the case with the mode as we just saw in that example. The mode is the only measure of center that is not unique. In other words, we can have more than one mode for a set of data. I was referencing bimodal data and multimodal data earlier. So that's another unique feature of the mode. And then finally, and this is what I think is the most important, the mode is the only measure of center that can be found for all 4 levels of data measurement. So if we're given nominal level data, where the data is just words, where you have the highest frequency data value could be a word, that word would be the mode. All right. So the mode can be addressed, can be used for all 4 levels of data measurement. It's the only measure of center that has that property. So the mean, median, and mode are all quite common. Let's take a look at a measure of center that you maybe haven't seen before, called the mid-range. This is the least known of all the measures of center. So let's go ahead and define it here. The mid-range, denoted by MR, is the midpoint of the minimum and maximum values in a set of data. So in other words, to have a minimum and maximum, the data has to be numerical. So it has to be either interval level or it has to be ratio level data. So here's the formula. What we want to do is to take the minimum value, add it to the maximum value, take that sum and divide it by 2. So you can think of it as kind of finding the midpoint of the length of the set of data, the midpoint between the minimum and maximum. All right. So let's go ahead and try one of these. Here's our set of data we were working with earlier. Let's go ahead and find the mid-range for the radiation levels for these cell phones. All right. So first, let's take a look at the data and find the minimum and maximum. And we went through this before when we were doing the median. Let's see, 0.38. It looks like it's the smallest number. And 1.55 appears to be the biggest. So let's go ahead and grab our calculator here and compute this. StatCrunch doesn't do mid-range, so you're going to have to do this yourself. So I just click on the fraction button, the fraction template button. We'll put in 0.38, and then we'll add in 1.55. That's the largest data item. Hit the right cursor key and then divide by 2. Go ahead and hit equals, and then I'll hit the SD key to put it in decimal form. So we get what? 0.965 as the mid-range of the data. So let's go ahead and verify that. So there's our screenshot, just exactly what we determined here. So the mid-range is 0.956 kilowatts per hour. So let me talk about some of the features of the mid-range here, because it has some unusual properties as well. Since the mid-range uses the minimum and maximum values, it's very susceptible to outliers. No measure of center is more susceptible to outliers than the mid-range. Consequently, we say that the mid-range is not a resistant measure of center. It can be easily thrown off by outliers. The advantages of the mid-range: first, it's easy to compute. It adds another measure of center to our repertoire, so to speak. And it avoids confusion by defining the mid-range along with the median. And another thing, I like to call the mid-range the measure of center of last resort, because sometimes you may be given some information where you're only given the smallest data item and the largest, and the mid-range would be the only measure of center you could determine for that. So let's talk about how we compute these measures of center using StatCrunch. So here's what we do. To compute measures of center using StatCrunch, first, enter the sample data in var1. Now, sometimes you have to enter it manually, but many times you can use that copy icon and open in StatCrunch. Second, to get the measures of center that we want, we select the Stat button, select Summary Stats, and then Columns, all right? Because our sample data will be listed in column form. Then we select the column in which the data lies, and then select the desired measures using the Control key from the statistics box, because there's all sorts of summary statistics we can compute. We just want the measures of center right now. And finally, click on Compute, and that'll give us our proper output. So let me just give you one note here. StatCrunch computes the mean, the median, and the mode, but doesn't compute the mid-range, but it does give you the minimum and maximum values from which you can find the mid-range, just like we did with our calculator. So let's go ahead and try one of these. We'll try a couple of them. We'll do study plan exercise 3.1.21 and 3.1.27. So let's go ahead and get started on those. So in study plan exercise 3.1.21, it says a sample of blood pressure measurements is taken from a data set whose values measured in milligrams of mercury are listed below. The values are matched so that the subjects each have systolic and diastolic measurements. Find the mean and median for each of the two samples, then compare the two sets of results. And then we want to know, are the measures of center the best statistics to use with the data, and what else might be better? All right, so let's take a look here. When you're taking a blood pressure measurement, the systolic value is the top number, the diastolic is the bottom number. So let's go ahead and open this data in StatCrunch now. So I'll click on the copy icon and select Open in StatCrunch. So we see we have 10 measures of blood pressures here for the systolic and diastolic measures. So the first thing we want to do is to compute the mean and the median. So let's go ahead and get started on that. So we'll hit Stat, Summary Stats, Columns. And we want to select both of these sets of data. So I'll hold down on the Control key on my keypad and select systolic and diastolic. And we said we wanted both the mean and the median. So once again, I'll hold down on the Control button on my keyboard and select mean, and then scroll down here. Oh wait, I didn't want the sample size. Let's get rid of that. Let's try it again. Mean, scroll down, median. There we go. That's what we're looking for. So we'll go ahead and click on Compute. And so we have four numbers, the mean and the median, for both the systolic and diastolic pressures. So the first part asks for the mean for both of these blood pressures. So that's these columns right here. So the diastolic blood pressure for the systolic blood pressure, median, is 125.1. And what do we have for the diastolic? That is 74.7. Looks good so far. And let's just go ahead and fill in the medians now. They are 124 and 76.5. And notice here, since the data set is an even number, the sample size of it, we had to take the middle of the 5th and 6th data values. Go ahead and check that. Very good. And then it says compare the results and choose the correct answer below. So we see here that if we analyze the output, that the mean and the median of the systolic blood pressures are both higher than those of the diastolic blood pressures, and that's what we typically expect to see. So let's see if we can find that answer in our choices here. Part A says the mean and median for the diastolic pressure are both lower than the mean and the median for the systolic blood pressure. Well, that's exactly true. That's kind of the converse of what I just said. So it looks like we don't have to go any further. The choice is A here. Okay, let's move on. And then it says, are the measures of center the best statistics to use with these data? So let's take a look at the solutions here. Part A says, since the systolic and diastolic blood pressures measure different characteristics, a comparison of the measures of center doesn't make sense. Well, that's what we did in Part A, and there's some validity to that. The systolic blood pressure measures one thing, diastolic a different thing. Since the sample sizes are large, measures of center would not be a valid way to compare the data sets. That's Part B for choice B. But notice the sample size is only 10, so that can't be true. Since the systolic and diastolic blood pressures measure different characteristics, only measures of center should be used to compare the data sets. Well, that's not true. There's some other measures we can also talk about. And finally, in choice D, it says, since the sample sizes are equal, measures of center are a valid way to compare the data sets. Well, the fact that the sample sizes are equal really has nothing to do with it. So it looks like Part A, choice A, might be our best choice here, huh? Okay, very good. And then one more part here. Let's take a look at that. And it says, what else might be better? So in choice A, it says, because the data are matched meaning systolic and diastolic in terms of the measurements, it would make more sense to investigate whether there's an association or correlation between the two blood pressures. That's a good answer. Since the measures, in choice B, since the measures of center are appropriate, there would not be any better statistic to use in comparing the data sets. Well, that's not quite the case. There's some other things we can look at too. Because choice C, because the data are matched, it would make more sense to investigate any outliers that do not fit the pattern of the other observations. There's probably a case for that. That's really not the best answer though. Since the measure in choice D, since the measures of center would not be appropriate, it would make sense to talk about the minimum and maximum values for each data set. Well, that invites being misled by outliers. So it looks like I would guess choice A might be the best one here. There we go. All right. So that is study plan exercise 3.1.21. Now we also want to take a look at exercise 3.1.27. It says refer to the data set of body temperatures in degrees Fahrenheit in the accompanying table and use software or a calculator to find the mean and median. And the question is, do the results support or contradict the common belief that the mean body temperature is 98.6 degrees? So let's take a look at this sample data here. So we'll click on the data icon. Oh, we see there's a lot of data here, so we definitely want to open this in StatCrunch. We don't want to enter all this in our calculator. So I'll click on the copy icon and then click on open in StatCrunch. So here's the sample data that we have, and what we want to do is to compute the mean of this data. So I'm also interested in to know what the sample size is too. So I'll click on Stat, Summary Stats, Columns, and that data is in var1, the very first column. And I said I wanted to get both the sample size n, so I'll click on n, and we also need the mean, so I'll hold down the Control key on my keyboard and click on mean. Go ahead and click on Compute, and notice here we had a sample size of 48, fairly large, and the mean is 98.1, and notice here all of the data values are written to 1 decimal place, so we want to round our answer to 2 decimal places. And as you see in the instructions, it also says to round the solution to 2 decimal places. So that would be 98.18 degrees. So far so good. And we want to find the median now. So Easy enough. We'll go ahead and do the same sort of thing. We'll go ahead and click on Stat, Summary Stats, Columns, click on var1, and now we want to scroll down to the median. There it is. Go ahead and click on Compute, and now we get a little box for that solution, 98.15. And again, the sample size was an even number, so we had to take the mean of the two middle values to get the median in that case. And then finally, it says, do the results support or contradict the common belief that mean body temperature is 98.6 degrees Fahrenheit? Notice here, if we examine the output, both the mean and the median are less than 98.6. They're both about, half a degree lower than that. So since both of these measures of center are below, this really kind of contradicts the belief that the average body temperature is 98.6 degrees. So I guess that's choice A in this case. There we have it. And so that's how we can analyze data, by examining these measures of center. So that concludes part 1 of Section 3.1, Measures of Center.